Thank you very much, Brent, for the introduction. Good day, everyone. So I'll be looking at spiral plant economics. So there are a couple of issues that we will be looking at. There's mass yield, or product quality, or spiral life. Sometimes the plant metallurgists want all of them, and there are times when getting all of them is impossible, where you have to either go for one which is mass yield, or you choose that you may have to go for product quality, or at times you have to choose for spiral life. So I'll go through 3 case studies. One case study will look at lifespan issues on a MG chrome plant. And the second case study will look at a mass yield issues on UG2 chrome plant. And I'll finish off with a case study on product quality issues on a coal washing plant. So when our spirals, the green spirals, when they're new and everything has been just been installed on site, everything looks quite nice. And as you can see on this image, it's looking very good, and it's a beautiful picture. But after some time in operations, things start changing. And let's get through the lifespan and see what really happens sometimes. So the lifespan of a spiral is estimated to be between 5 to 7 years in chromite and about 8 to 10 years in coal processing. And what we have realized over the years was that the lifespan is mostly an issue that arises in LG, MG wash plants, and especially when there's no milling, or where there's no milling, and where you find that the plant there's just crushing only, especially where the crushing is done in an open circuit. And we have also figured out that it also becomes an issue in metal recovery in ferrochrome. So what could be the issue? We realized that the coarse particles are a big problem in spirals. So when you feed material onto a spiral, the specific gravity and particle size plays a very huge role in particle separation. But there are also other parameters that influence separation. So what you would find is, as the material slides down the spiral, you will have the fine heavies, as you can see on the picture on the left there. The fine heavies will report towards the inner side of the spiral. And then as you move outwards, you will have the fine lights, the coarse lights. And what is interesting here, the very coarse lights, you will see them on the outside of the spiral, and as well as the ultra fine heavies and the ultra fine lights. You will see them on the outer side of the spiral. So on the right side of the slide here, you can see on the image there, what the image illustrates with the red dots. That's where we could pick particles that are largely greater than 2 millimeters on the trough. And what you can see is that you have got a high concentration of coarse particles on the outwards of the trough, which also implies what I've mentioned before. And on the outside of the trough, what you have got very high particle velocities. It's more of the turbulent region. And as you move inside of the trough, then you have got the sort of laminar flow type. So in one of the plant, if you can look, on the PSD, shown in this case, in this plant, that after crushing, feeding onto the spiral section, that this type of a PSD where almost about 89% was passing 1000 microns. So what the client decided to do, they were running with a 1 millimeter aperture panels, and then with 1 millimeter aperture panels, they then thought that they could be losing about 10% of plant feed as they are throwing away, that they were throwing away that oversize. And another thing with this material, the greater than 1 millimeter size had a chromite grade of around 25%, and the less than 1 millimeter had a chromite grade of above 30%. So the less than 1 millimeter was basically more sweeter. And then with this operation, they felt that, I mean, with the mess yield that they were losing, they decided that if they could install like 1.4 millimeter aperture panels, so that they can increase the plant feed tonnages. And indeed, the plant feed tonnages increased. But then, as I showed you, that the greater than 1 millimeter had low grade, so they then also started experiencing product grade control challenges. And another issue that came upon was the short spiral lifespan. And then they also moved to, I mean, to an aperture size of 1.2. So what I will show you the impact on the spiral when they were running with the 1.4 millimeter aperture panels and when they were running with the 1.2 millimeter aperture panels. So in this section, with the 1.4 millimeter aperture panels, with about 4 to 6 months into operation, you can see what had happened on the spiral on the outside, on the outer side. This is the side where I indicated that it's got very high velocity. So, and when you look on the inside, where there's typical laminar flow, you don't have anywhere there. So the wear was happening on the outside, and with 4 to 6 months into operation, the spiral was, I would say, it was unusable. And with this plant, which was doing like 80 tons per hour, a 4-stage plant, rougher, scavenger, cleaner, and recleaner, the replacement cost of the spiral was sitting at around 2.5 million rand. So, which means every 6 months, they would have to spend about 2.5 million rand on buying new spirals. And this value excludes the installation cost that is associated with this. And then when they were running with the 1.2 millimeter aperture panels, 12 months into operation, so you can see on the images there that they started having holes on the spiral, and the holes are happening on the outer side of the spiral as well. So what could be the solution for this client? So what you needed was to, I mean, on the manufacturing side, we needed to add almost like 400% more spiral lining or PU lining, which also comes at an additional cost. I mean, to sort of improve the life of the spiral. But even with that, you weren't gonna get to the 6 to 7 years that I indicated for chromite operations, for UG2 chromite operations that I highlighted before. So does the additional feed and mass yield justify the replacement cost? So this is the thing that I would say the plant personnel need to go through, I mean, when making this type of decisions. And just to justify as well the impact that the cost material have on the spiral. I mean, in this picture, what we took is of a UG2 feed where 80% of the material is passing 75 microns. So on figure 8, that's where on commissioning, you can see the spiral surface is still looking green, everything is still looking nice. And then 6 years into operations, you can see that, I mean, you don't have the type of holing that we saw, I mean, on the previous slides here, because the particles that are being treated here, it's fine material. So you can see, I mean, the amount of life that you can get out of the Multotec spiral, I mean, if you're feeding the fine material. And if you look at that image B, you can see some marks there, and those marks are largely due sometimes to skates. So sometimes you also need to take care in terms of skates removal upfront, because they also have an impact on the spiral life, but not as much as we saw with the coarser particles or greater than 1 millimeter size particles that we saw before. So next on my case study is looking at mass yield on a UG2 chromite plant. So in this plant, they were feeding 244 tons per hour with about 11.4% chromite feed grade. And then out of 244 tons that they were feeding to the plant, they were only producing 14 tons per hour of concentrate. What happened to 230 tons per hour? This is going to the tailings. So here we could see that we have got a problem. You can't feed 244 and you lose almost 230 tons per hour. So normally during design stage of a plant, we specify that we need the deslamming cyclone need to deslime at around 45 microns. Because the issues with the slime, as I've indicated before, is that the ultrafine slimes as well, they move onto they run onto the outside of the spiral. So most of the time they end up in the tailings, and they also changes the viscosity of water as well, which also has got an impact in terms of separation. So we normally specify that the feed to the spiral should have less than 10% below 38 microns. Then let's see what was happening to the feed that we were feeding to the spiral. Why was 230 tons per hour going to the tailings? So when you look at the feed, at first we started by doing sampling around the cyclone section, the desliming cyclone. So with the feed going to the desliming cyclone, we found that we had about 53% passing 45 microns. And remember, we spoke about desliming at 45 microns. So, and then we also found that the desliming cyclone section, about 74 tons per hour was going to the overflow, which is almost 30% of the feed, which we are already losing right here at this stage. And then when you look at the assay by size as well of the feed, the plus 45 microns, the feed grade is sitting at 10.4, and then the minus 45 microns, the feed grade was sitting at 13.2. So on the minus side, on the minus 45 side, that's where you had, I would say, good quality feed as well. So, and then with 170 tons now going to the spiral, what was really happening on the spiral? So looking at, when we sample the tailings of the spiral with about 156 tons going to the tailings here in this section, you look at the assay by size, the plus 45 microns, it's now sitting at 7.2% chromite, and the minus 45 is sitting at 13.1. So if you go backwards, the plus 45, the plus 45 was sitting at around 10. Now it's sitting at 7.2. So you can see that separation was largely happening on the plus 45 microns. When you look at the minus 45 microns, the grade didn't change at all, which illustrates that the minus 45 microns, which is also a high grade section, wasn't separating on the spiral, which means much of it or all of it was reporting to the tailings. And it also adds on to why we were getting around 14 tons per hour, which is almost like 5% mass yield. So how do we solve this type of a problem? And that's where I'm gonna introduce the UF7, which is an ultra-fine spiral. It's a shallower 710 spiral, giving more residence time onto the ultra-fine particles. And with this spiral now, it allows one, instead of desliming, having desliming cutoff around 45 microns, it allows one to drop it to 25 microns. And also, as well, we have seen that the high chrome content was in the minus 45 microns. So we're gonna also, it allows us to give a chance to the minus 45 microns as well. And then hence we can then send more solids, can be sent to the spirals. And what we have found is that the UF7 spiral can handle the ultrafine material much better. And the test, what we did was to do tests, first at Multotec, which showed, an additional 6% mass yield that can be achieved. If we were to implement with this same material that we were running on the SC20 spirals on site. So what does that mean in terms of finances? So the 6% mass yield, it means you can almost get around an additional 19 tons per hour in terms of Kong for this same plant, set out. And in this case, I've excluded if you were to change the configuration of the desliming cyclone so that instead of desliming at 45, you deslime now at 25. So looking at this material with chrome price at around 1,200 tons, per ton, and with 400 operational hours per month, you're looking at an almost the difference of around 2.4 million rand per month, which over a year it's sitting at around, you could be talking about, I think, $2 million a year, which with the introduction of the UF7 spiral in this instance into this flow sheet, it will be a lot of money. And also the more you are adding to the tailings, the more cost you putting in terms of tailings management as well. So I will finish off with a case study on product quality issues that we also came across in a coal operation. And in this coal operation, what we were having, the client was having challenges in terms of the product quality. It was varying significantly. So in this case, the client was getting around 33% ash in the product, and they were aiming for below 20% ash in the product. And in this case, they've heard about the SX10 low-cut spirals that Multotec has. And so the client here thought that they wanted to go the route of the SX10 instead of the MX7 spirals. So they had thousands of tons of off-spec product that they had stockpiled. And in this case, the spiral plant mass yield was very high, but they were having an off-spec product. So when the client approached that they want to install the low-cut spirals, at first we had to do our own sampling on site to see if it was worthwhile to move to look at the low-cut spiral, or it was something that was related to the process around the plant. So we had to do sampling over a couple of days around the fine section of the coal plant. So, and in general, what you need to keep in mind, in coal, we normally try to keep the below 106 microns at below 10%, unlike in heavy minerals where we normally aim for 38 microns, as I mentioned before. So with the sampling that we did around, we sampled the feed to the desliming cyclone, the spiral feed, as well as the spiral product. And if you look in this case, if you can pay much attention onto the 106 micron size, on the feed to the desliming cyclone, we had about 56% passing 106 microns. And with that, if you look at the percent ash of that size fraction, it's sitting at around 55%. So you can see already that the 106 microns here, it's a big problem. With this feed. And then looking at the spiral feed after, which is the cyclone underflow, the cyclone had reduced that 106 to now almost 22%. And now you're sitting, this had also reduced the plant feed, the spiral feed ash to around 44% from 55. So you can look here the impact that the desliming cyclone was doing. It already reduced the ash from 55 to 44% by just desliming. And it also highlights the importance of desliming in coal as well. Especially where you have got high ash in the ultrafine section. And then when you look on the spiral product that was coming out of the MX7, if you still look on that, 106, the 106, fraction, the cumulative percent passing of it, the cumulative percent passing, it had now jumped to almost 44%. So that also tells us that the minus 106 fraction, it also is not separating on the spiral as well, because now you have got a huge fraction of it in the product. So it's running on the outside of the spiral, because the spiral product in a coal spiral, it collects on the outside. And then when you dig further, if you look, in terms of the total ash of the product, you're sitting at 33. And then when you look at the at the different assay fraction, you can see that on the plus 212, that's where you're sitting in the product itself. You're sitting at below 20. And then on the minus 212, that's where you're sitting at above 20. And in this case, you can see that that plus 212 and minus 212 fraction contributes a bigger portion of mass onto the product. So basically, I mean, the quick solution by looking at this, one can say if I were to screen this product again, maybe with a around 212, then you were already getting your product on spec. So basically, if you look here, the product was on spec, but the slimes were influencing the product quality. And what you can see is that the fines poorly separate on the spiral. So what is it that we had to do? We had to call in our, cyclone experts, Aaron, and look at the cyclone configuration where we changed so that we could send more of the bed fines to the overflow. But one needs to bear in mind as well that the more overflow you're sending as well, that might have an impact on your thicken as well. So it needs to be a full holistic, approach of the full plant as well. And then with that, we ended up now sending more of the below 202 microns onto the overflow. And as a result, we could get the product quality coming at around 17% ash. But in this instance, as you saw before, that you have got about 70% is below 212 microns. Then the overall mass yield dropped very significantly. But the good thing is the product was now coming on spec, but at a low mass yield. But now it's a sellable product. So the lesson we got out of the processing unit was it's very important understanding the assay by size as well as the washability. When troubleshooting product quality issues on a spiral plant.